All right, open up your book to section 8-3. We're on page 397 in your book. The title of this section is the Other Composite Argument Properties. We saw one of these in the previous section. We'll deal with the others here in this section. And actually, there's three different groups of composite argument properties we're going to deal with. So for trig functions f, we want to be able to derive and learn the properties for f of negative x in terms of f of x, f of pi over 2 minus x in terms of functions of x, and finally f of a plus b and f of a minus b in terms of functions of a and functions of b. So the properties here that we're going to talk about all deal with something other than just x that we're plugging into our particular trig function. The opposite of x, pi over 2 minus x, or a plus b or a minus b. All right, let's go back and refresh our memory a little bit first, which is dealing with the odd and even properties. If you recall, back in chapter 1, we've covered these properties, what it means for a function to be odd versus what it means for a function to be even. We said that an odd function has the property that f of the opposite of x is equal to the opposite of f of x, or another way of describing that graphically would be that it has point symmetry about the origin. And for an even function, algebraically we'd say that f of the opposite of x is equal to f of x, or graphically that means that you have line symmetry over the y-axis. So that's what it means to be an odd versus an even function. And remember, there's also a third category here of none of the above or neither. Many functions that we look at are neither odd nor even. When it comes to your trig functions, though, turns out that all 6 of your trig functions fall into one of these two categories. And it turns out that if a function is even, then its reciprocal is also going to be even. Or if a function is odd, then its reciprocal is also going to be odd. So that's the reason why you see the two categories like you see here. Cosine of the opposite of x is equal to cosine of x, and the reciprocal of cosine is secant. So that means secant is also going to be an even function. Secant of the opposite of x is equal to the secant of x. If you think of your graph of the cosine function, or the secant function for that matter, the graph has symmetry across the y-axis. If you do a horizontal reflection across the y-axis, you'll end up with the exact same graph that you started with. It's an even function. On the other hand, we have 4 odd trig functions. And the first one there is that the sine of the opposite of x is equal to the sine of x. And, it's the opposite of the sine of x. And since sine is an odd function, that means it's reciprocal. Cosecant is also odd, so the cosecant of the opposite of x is equal to the opposite of the cosecant of x. And again, if you think of the graph of your sine function, or cosecant, and you take that graph and you rotate it 180 degrees about the origin, you'll end up with the exact same graph that you started with. Or that would be the same as reflecting across the x-axis and then the y-axis, and you'd end up with the exact same thing that you started with. It's an odd function. Tangent is also an odd function. Tangent of the opposite of x is equal to the opposite of tangent of x. And again, since tangent is odd, that means its reciprocal is also odd, so cotangent of the opposite of x equals the opposite of cotangent of x. There are the 6 odd and even properties there for our trig functions. For all these properties that we're going to look at, the next question is, well, can we actually show that that is in fact the case? Can we prove those properties? Now, we're not going to go through and try to prove all of these properties, but we will definitely tackle a couple of these. And once you see how a couple of these are proven, you'll be able to show that the others are going to follow the same way. So let's deal with cosine. Let's take one of the even functions and show that it is an even function or show that it has this property of being even. So if I've got a point UV here, and I've just sketched this on a circle with a radius of r, and I've marked the angle as x, I've also sketched where the opposite of x would be then, that angle. And the corresponding point there would be u and then the opposite of v. It's the same horizontal component, but the v is the opposite. So look what happens when we take the cosine of x. Just go back to your definition. If you take the cosine of x, that of course is equal to u over r. And if I'm trying to show that the cosine function is an even function here, then I need to also find out what the cosine of the opposite of x is equal to. And the cosine of the opposite of x is equal to still u over r. So notice that we get the exact same thing. So since the cosine of x is the same as the cosine of the opposite of x, this is exactly what it means to be an even function. So cosine is even. Let's do the same thing for sine. If I take the sine of x we know from our definition is v over r. And now take a look at what the sine of the opposite of x is equal to. If I take the sine of the opposite of x, that's that angle that's down below the x-axis there. That's going to be the opposite of v over r. Notice that I get the opposite answer. This is the same as the opposite of the sine of x. The opposite answer that I got up above. And that's exactly what it means for us to be an odd function. This is odd because it has that property. The sine of the opposite of x is the same as the opposite of sine of x. And you can go through for the other 4 trig functions and show the properties the exact same way as this is done, and you'll end up with showing that all 6 of these are either odd or even functions. All right, let's take a look at an example here. Example on page 397 asks us to do a couple of calculations here. Just to verify these properties really is all we're doing. Let's start with cosine. It says to find the cosine of the opposite of 20 degrees and the cosine of 20 degrees. Now, if cosine is in fact an even function, like we're claiming that it is, then we should find that we get the same result. So let's see what happens here. Go ahead and grab your calculator. And we are in degrees here, so let me switch over to degrees on my calculator. And we'll take the cosine of 20 degrees and the cosine of a negative 20 degrees. And again, since we're claiming this is an even function, I'd expect to see that I get the same result, and that looks to be the case here. Let's grab a picture of that. We'll just put that on that slide. All right. So that, in fact, is an even function. Let's try that out with sine and see what happens. So let's take the sine of 20 degrees. And now, again, if sine is, in fact, an odd function, then I'm going to expect that I get the opposite answer here when I take the sine of negative 20. And there we go. We got the exact same value, just they're opposite of each other. And we'll paste that. All right, there we go. We've got ourselves a couple of examples to illustrate that these are odd and even. Of course, these don't prove that they're odd or even. The work that we did on the previous slide proves that cosine and sine are even and odd functions. But this just kind of helps us justify that that is in fact the case. All right, there's another set of properties I want to talk about, but first let's deal with a couple of terms here. Hopefully we recall these terms here, but the first one is complementary angles. We have complementary angles, and then we also have supplementary angles. Complementary angles are two angles whose sum is 90 degrees, or that would be pi over 2 radians. Supplementary means that they add up to 180, or that would be pi radians, 180 degrees or pi radians. But we're dealing with complementary angles. So their sum is 90 degrees or pi over 2 radians is what we're going to deal with here. And the property that I want to look at with you is what's called the cofunction property, and this is where the names of our trig functions come from. They are written in cofunction pairs. And so the cofunction pairs, we have sine and cosine, we have tangent and cotangent, and we have secant and cosecant. Those are the cofunction pairs. This is really where the names come from. And the reason that we have a cofunction for each one of the functions that you see over on the left. So we have the following cofunction properties. And the cofunction properties come about because these are cofunctions of complementary angles. So it's the CO from complementary that's producing the term cofunction here, and why we name these accordingly. But here you go. It turns out that if you take the sine of x, that's the same as the cosine of pi over 2 minus x. Or over on the right, you could do it the other way around. You could take the cosine of x, and that's the same as the sine of pi over 2 minus x. On the next row, we have tangent of x is equal to the cotangent of pi over 2 minus x. Or you can swap the two trig functions there. Cotangent of x is the same as the tangent of pi over 2 minus x. And finally, on the third line there, we've got the secant of x is equal to the cosecant of pi over 2 minus x, or that's the same as the cosecant of x is equal to the secant of pi over 2 minus x. Again, notice that those are written in cofunction pairs. So that top row is sine and cosine. The second row, we've got tangent and cotangent. And the third row, we've got secant and cosecant. These are the cofunction properties. And furthermore, if you think about the two angles that you see there that we are dealing with in each one of those properties, those are actually complementary angles. If you take the angle that you see on the left of that property, that is just x, and the angle that you see on the right, that's the pi over 2 minus x. If you take those two angles and you add them up, you're going to end up with pi over 2. So in other words, when you look at these two angles right here, this guy here and this guy right here, those are complementary angles. This is where the term cofunction comes from, and this is why we name them, these functions, the way they are named. One thing to note here for degrees, of course, switch over to degrees by letting pi over 2 radians be 90 degrees, and you can write these same properties in degrees. I'm not going to write all 6 of those down, just do a conversion there. But again, let's take a look at the proof of where these come from. And again, I'm not going to prove all 6 of these, and I'm certainly not going to go through the proof of the 6 you get from degrees either. We'll focus on radians and realize that the degrees will follow the same way. And furthermore, once we see how a couple of these are all set up, you should understand how the rest of these properties. So let's take the first line that we saw there. We're dealing with sine and cosine. And I've got myself a right triangle here. The nice thing about working with a right triangle, once you set up a right angle down here, that angle right there is pi over 2, which means that the other two angles, these two guys right here, have to add up to pi over 2. Or if you're in degrees, then they have to add up to 90 degrees. That means on a right triangle, you're guaranteed that the two non-right angles are complementary. And so this is where this property actually comes from. Let's start out with sine of x. If I take the sine of x, that's my angle down there at the bottom left, and sine of x, of course, is v over r. This is equal to v over r. And now let's use the cofunction. So instead of sine, let's use cosine. And let's use the other angle, which turns out to be its complementary angle, that is pi over 2 minus x. And now when I take cosine, of course, is the adjacent over hypotenuse. When I take the adjacent side, that's v over r. And notice we get the exact same thing here, v over r in both those cases. So that means sine of x and the cosine of pi over 2 minus x must be the same thing. Let's do the cofunction property the other way around as well, just so we can see that it does in fact work the other way. So let's take the cosine of x. The cosine of x, from our little triangle there, cosine of x over there in the bottom left corner is our angle x. So cosine of x would be u over r. That's the adjacent over the hypotenuse. And now use the cofunction, so sine instead of cosine, and use the complementary angle, the other angle, which is the pi over 2 minus x. Sine is the opposite, so the opposite side of that angle is the u, divided by the hypotenuse, which is r. And again, notice that we get the same thing. In both cases here, we got u over r. These are the same, so that means those two must be equal to each other. That is our cofunction properties for sine and cosine. And of course, the other four properties will follow with the exact same technique here. All right, so let's take a look at an example here again, just to verify this property. Let's take a look at what the sine of 20 degrees is equal to. And we'll also look at the cofunction to sine, which would be cosine, and the complementary angle to that, so 70 degrees. Let's check to see what we end up with. Again, if this property is true, then that means we better get the same thing when we do this calculation. So let's try that out. Grab your calculator, and let's take the sine of 20 degrees. And let's take the cosine of 70 degrees, which I guess we did already calculate the sine of 20 earlier, but we've recalculated. If I calculate the cosine of 70, again, we should not be surprised because of this cofunction property that we get the exact same thing. Very nice. All right, the last set of properties are the composite argument properties, is what these are referred to. And the composite argument properties, there's actually 6 of these, just like we've seen for the other sets of properties. There's several of them. And we've actually already seen the first one. We actually went through and proved that very first one in the previous section. We proved that the cosine of the quantity a minus b is equal to the cosine of a times the cosine of b, plus the sine of a times the sine of b. There also is a composite argument property for cosine of a plus b. If you change that to addition there, cosine of the quantity a plus b, it turns out that you end up subtracting these two quantities. So it's the cosine of a times the cosine of b minus the sine of a times the sine of b. With cosine, realize that the sign changes there when you look at the property there on the left side versus the right side. That is, it starts out with addition here, but changes over to subtraction here. Or it's subtraction over here, and it switches to addition over here. Just remember, with cosine, it changes the sign there. All right, we also have composite argument properties for sine. That is, if you take the sine of a minus b, it turns out to be the same as sine of a cosine of b minus cosine of a sine of b. That's very similar to our properties with cosine, but realize that your sine and cosine now are kind of split apart. They're not split apart, but they're combined there. You've got sine and cosine that you're subtracting from a cosine times sine, versus having the sines and cosines grouped together. So sine of a minus b is equal to the sine of a minus the sine of, times the cosine of b minus the cosine of a times the sine of b. Notice in this case that your signs there stayed the same. So here we are subtracting, and over here we're subtracting. With sine, the signs stay the same. And if I take the sine of a plus b, we probably can guess at this point, based on what we've seen up above, that we're probably going to end up with the same thing except they're added together, and that's what we see there. Sine of a cosine of b plus cosine of a times the sine of b. So if we're adding here on the left, we turn it out to be adding over there on the right with sine. The signs stay the same there. All right, and the last set for us to talk about are the composite argument properties for tangent. And tangent we know is equal to sine over cosine, and actually these come directly from the properties up above. Just simply take the sine of a minus b and divide it by the cosine of a minus b and do some simplifying and rewriting, and you'll end up with what we see over here on the right. But it turns out that the tangent of a minus b is equal to the tangent of a minus the tangent of b. So notice that your signs there stay the same in the numerator, but it's divided by 1 plus the tangent of a times the tangent of b. So the sign changes in the denominator. Now again, if you think about where this property is going to come from, the fact that it's the tangent is equal to sine over cosine, if I look up above at my sine property says that my sine stays the same. So if I'm subtracting tangent over here on the left, I would expect in the numerator that I'm also subtracting, because that's the sine part of this. On the other hand, cosine, if I scroll up a little bit, cosine, the sign changed. It went from subtraction to addition. That's the same thing I'm seeing here in the denominator. I was subtracting on the left, but I'm adding down in the denominator. That might help you remember to get the right signs in this property here when I need to use it. And like we've already seen here in the previous properties, if I can do this with addition or subtraction, I can do it with the other one. And so that's what we see here. If I've got the tangent of a plus b, I can rewrite that as the tangent of a plus the tangent of b. Again, notice that the signs stay the same there in the numerator, because the numerator is the sine part when I use my quotient property to rewrite tangent. And that's all divided by 1 minus the product of tangent of a times the tangent of b. Now we're going to tackle the proofs of these in the second half of this section, so we're not going to deal with proving these 6 properties, but we will eventually prove these 6. We've already proven the very first one, and we're going to use that property to help us prove these other ones. So we won't have to go through the same amount of work we did to prove the very first one, but we'll still go through and prove each one of these. All right, and that's the end of the first part of section 8-3.